Buenos días todos. Me llamo Eric Anglaret, soy de Montpellier, Francia. Más disculpe, más no puedo hablar español. Entonces, the following will be in English. So I ask Fernando to tell me if I am too speed in English, but please, all of you, make me a sign if I accelerate, okay? Because my usual rhythm is quite speed, so please let me know if it's too speed. And if my English is not, if you cannot understand, please ask me and I try to repeat in French or in Spanish. So today we will talk about electronic and optical properties of carbon nanotubes. I don't know if all of you attended the course of Vincent Jourdain. Did you attend the course of Vincent Jourdain on the structure of nanotubes? Did you see that? Yeah, you could see that? Okay, bueno. So usually lots of people heard about nanotubes because whatever the field you work in, you heard that they have exceptional properties. So probably you know that depending on their structure, they can have different electronic properties. So we will work on that today, see what is the relation between their structure and their electronic properties. What nanotubes are metallic, what other nanotubes are semiconducting. The other electronic properties of interest are, as far as metallic is concerned, the very high current density that can flow along the nanotube, which is much higher than that which can flow along a copper wire. They are also known to be high thermal conductors, much better than diamond, which is one of the highest conductor, one of the better conductor. When you have semiconducting nanotubes, they have interesting optical properties. Their gap is in the near infrared, close to 1 electron volt, so you can have light emitters in the near infrared. We will talk about this property tomorrow. They also have interesting mechanical properties. Their Young modulus is about 1 terapascal, which is also quite exceptional. And other properties of interest, like the property of emitting electrons. When you apply a field to them, because they are very thin, you can extract high intensity electron beams from their tip and use them as field emitters. So because of these properties, people expect many applications from nanotubes, and we can separate the applications between 2 levels. The first level is the level of 1 molecule, 1 individual nanotubes. So at this level, people expect interesting things in the world of electronics, optoelectronic devices. One knows how to prepare transistors or diodes with nanotubes. Obviously, there are issues to develop that at an industrial level, but at the lab level, people already know how to prepare electronic components with nanotubes. Because they are very sensitive to their environment, you can use them as sensors, because when they will absorb gas, it will change their electrical conductivity or their optical properties. So you can imagine different kind of sensors with them. Because of their mechanical and electrical properties, people developed microscope tips, near-field microscope tips with nanotubes. And because of their optical properties, you can use them as fluorescent markers, for example, in biological media. For drug delivery, you can follow their trace because of their optical properties in a human body or biological cells. And then you can shift at a larger level, at the level of the macroscopic world, and you can use them as charts in composites. Once again, you can use many of their properties and try to transfer these properties to different kinds of matrices. The most used matrices are polymer matrices, but we can also prepare nanotubes dispersed in metal matrices, or in ceramic matrices, glass matrices. And once again, you will try to use their mechanical properties to strengthen the materials, or their electrical properties to evacuate electrons or evacuate heat, or their optical properties to make multifunctional materials, which could be strengthened mechanically, but also have optical properties. And thanks to their field emission properties, you can use them to send electrons on screens and make field emission displays. So the first nanotubes were observed officially in the beginning of the 90s, so it's now more than 20 years. And lots of researchers have worked hard on that, so lots of things are well known now, but there are still some challenges. The first challenge is about synthesis, because we know how to prepare nanotubes, but it's still quite expensive. So if you want to go to industrial development, you have to decrease the cost, and for that we have to find, to ameliorate the process. Also, if you want to have high purity nanotubes, you have to develop the best catalysts, the best gaseous precursors, to find the good thermodynamic conditions. Especially, you have to decrease the temperature at which you prepare the nanotubes to decrease the cost. But if you want to decrease the impurities, it's better to work at high temperature, so you have to find the compromise to have good quality of nanotubes at small cost. Another big challenge, and this is especially a challenge when you want to use them as electronic components, is to work with only one class of nanotubes. When you grow nanotubes, and the course of Vincent was focusing on this point, when you grow nanotubes, you always have a mix of metals and semiconductors, and you always have a mix of different diameters. But when you want to control the property of one transistor or one light emitter, you would like to work with one unique class of nanotubes with a well-controlled diameter and either a metal or a semiconductor, depending on the application you wish. So there are lots of works on the separation of nanotubes. You can try to optimize the growth condition in order to favor the growth of one particular class, but you can also work afterwards and develop chemical conditions, chemical processes where you will be able to separate the different classes. Now, when we come back at the scale of the composites, one big issue is processing composites. First, you have, if you want to have a high quality composite, you have to find a way to disperse the nanotubes homogeneously in your materials, and that's not that easy because they used to be attracted by van der Waals interactions to stick to each other, and to form nanocrystals. So it's not that easy to separate them and to distribute them in a sample without destroying them. And obviously, when you look at these materials, you see that they are very anisotropic, and therefore, most of their properties are also very anisotropic. When we say that they have very high Young modulus, it's only in the axis of the nanotube that you find this property. When you say that they can conduct high density of current, it's also only in the direction of the axis. When you say that they emit light, it's only with light polarized parallel to the axis. So all the properties are very anisotropic. If you want to take advantage of this property, you have to find a way to align the nanotubes in the composites. And that's also not that easy. So the course will try to give some answers to these challenges. And we will especially focus on optical spectroscopies, which are widely used as powerful tools to study not only the optical properties, but also the electronic properties. And you also have information on the structure of the nanotubes when you use these spectroscopies. So this course will be mainly focusing on how optical spectroscopy can help to get information on structure, electronic, and optical properties of nanotubes. So these are the different parts of the course we will try to detail. This is the outline of the course. So this morning we will start by recalling what is the structure of a nanotube. We will not go into detail because you had this course from Vincent Jourdain the week before, but we will recall some main results. And then we will try also to practice on this kind of sheets. So for those people who are in a visio conference, they don't have this sheet, but there will be the slide corresponding to a graphene sheet where we will be able to work on what are the vectors, the unit vectors describing the lattice parameters of nanotubes. What is the relation between these vectors and the number of hexagons or the number of carbon in a unit cell? And then at the end of the course today, we will try to relate the structure to the electronic properties. And then, either at the end of the course today or tomorrow morning, we will relate the electronic properties to the optical properties. When we will know about electronic and optical properties, we will see what are the optical spectroscopic techniques that are used to study characterized nanotubes. These are especially absorption techniques, scattering techniques like Raman scattering technique, photoluminescence technique. So you can use the properties of absorption, scattering, emission of light from the nanotubes to study them. And we will see what are the different applications of these optical spectroscopies in terms of understanding the structure, the electronic, the optical, the thermal properties of nanotubes. So these are the different goals of these courses, what I would like to transfer to you. And we will start right now about the structure. So the question is, how can we describe accurately the structure of one nanotube? Here, on the corners, on the edges of the slide, you see two kinds of ideal nanotubes, which form two different families. On the right, a la derecha, es un single wall nanotubes, una única pared. And on the left, a la izquierda, it's a multi-wall nanotubes with different layers of graphene rolled up around the axis. Usually, people compare this structure to Russian dolls, where you have different structure, one around each other. In this course, we will mainly focus on the single-wall nanotubes, because it's the ideal nanotubes, the ideal object. And we won't have time to go into details of the properties of these multi-walls, which are obviously much more complicated because they associate the properties of the different layers, and you have to control the diameter and chiral angle of the different layers to understand well the properties of this kind of object. As far as applications are concerned, these ones are much more expensive, much more difficult to prepare, so they would be used for, how do you say that in English? For properties that require very accurate things, accurate and high standard properties, like for electronic or optical devices. And these ones are much cheaper to produce. Usually they contain higher density of defects. the structure is not that much controlled, that much well controlled. So these ones are more for large volume applications, like for example in composites, where you don't need to control exactly the structure. You just need to have a distribution of charge with average properties and not high standard properties. So once again, I will focus during this course mainly on this kind of ideal single-wall carbon nanotubes. So this is a recall of the course of Vincent Jourdain. So in the carbon world, you can find different kinds of structures and different kinds of dimensionalities. The most old one, the older one, which is actually the only thermodynamically stable phase of carbon, is graphite. So the name of graphite was given at the same time than the French Revolution in 1789. The graphite is made of graphene sheets, which are hexagonal arrangements of nanotubes with sp2 bonds, which are superimposed one to each other with van der Waals interactions. Then researchers discovered in 1985 carbon molecules, which are called fullerenes or buckyballs, the most well-known as 60 atoms of carbons and as from the shape of a soccer ball. And there was a Nobel Prize for this discovery in 1996. In the beginning of the 90s, people observed carbon nanotubes, which can be seen as the rolling up of one single graphene sheet. And at this time, theoreticians said that one single graphene sheet was not stable. So people didn't expect in the beginning of the 90s that 10 or 13 years later, we would be able to separate one single graphene sheet and make very interesting physics on that. So this slide describes how, in your mind, you can imagine to prepare a nanotubes. Obviously, in the reality, nanotubes are not formed like that. They are usually formed by CVD techniques, where you decompose a gas on a catalyst particle, and you will dissolve the carbon in the atom, in the metallic particles, and then when you will reach saturation, you will have a nucleation of a carbon shell, and then a growth of the nanotube on the catalytic particle. But in your mind, the most easy way to imagine to form a nanotubes is to take a flat graphene sheet, to cut one piece of this graphene sheet, and then to roll it up to form a cylinder, this way. But when you see the symmetry of your graphene sheet, you can easily imagine that there are many ways to cut the graphene sheet and then to roll it up. And depending on the way you cut the graphene sheet, you will have different properties, especially different electronic and optical properties. So, to define the way you cut the graphene sheet, you will use two vectors. The most important vector is written here, CH. We will call that the chiral vector. This chiral vector will correspond to the circumference of the nanotubes. So this chiral vector, when you will roll up the graphene sheet, will come here as the circumference of the nanotubes. So the choice of the chiral vector will fix the diameter of the nanotube. There is a simple relation between the chiral vector, the norm of the chiral vector, and the diameter of the nanotube. And this chiral vector, you can express it in the lattice of graphene. So this is an hexagonal lattice. To describe this hexagonal lattice, you need two vectors, which are here called A1 and A2. The norm of these two vectors is the same. and the angle between the two vectors is 60 degrees. So any vector in the graphene sheet can be defined as a linear combination of these two lattice vectors. So the chiral vector can be expressed as NA1 plus MA2, where N and M are two integers. And because all the properties of the nanotubes are defined by this chiral vector, usually you will refer to a nanotubes using this NM parameter, NM integer. So in the following of the course, we will usually speak about a 10-0 nanotube or 5-5 nanotubes, and this will refer to this chiral vector. When you know this integer, N and M, you can calculate the diameter from this relation, and you can calculate another very important parameter, which we call the chiral angle, and we note it theta. Theta is actually the angle between the chiral vector and the direction of one unit vector, let's say A1. So theta is the angle between A1, this is the direction of A1, and the chiral vector. And theta is directly defined by N and M, the two integers which allow to define the chiral vector. So, just to fix the ideas, I would like to work with you on the sheets I distributed, just to draw one unit cell of nanotubes and to calculate the relation between NM and the number of hexagons, which will be an important parameter when you play with electrical properties, electronic properties. And we will also calculate together the number of carbon atoms in a cell unit, in a unit cell, sorry. And then we will conclude on the structure of nanotubes. So before to start that, I would like you to observe this part of the slide where we defined the unit vectors of the graphene sheet and where we define here one unit cell on the graphene sheet. So I would like you to tell me how many hexagons and how many carbon atoms you can find in one unit cell of graphene. So according to you, how many hexagons do you have in one unit cell? Maybe you can use your sheet to see that. I would like you to tell me how many hexagons and how many carbon atoms you have in one unit cell, defined by the A1 and A2 vectors. So how many hexagons, according to you? Who wants to answer? Maybe we can start by something more easy, the number of carbon atoms. How many carbon atoms do you observe in this cell? 2. Thank you. There are 2 carbon atoms per unit cell of graphene. And how many hexagons? Compare the surface of this unit cell with the surface of one hexagon. How many hexagons do you find? You can see that there are not many hexagons. How many hexagons do you see in the unit cell? Yes, you see one hexagon. So in the unit cell of graphene, you have one hexagon and 2 carbon atoms. Okay? So now we will make the same exercise, but not in the unit cell of graphene, in the unit cell of one carbon nanotube. And we will take 4 examples. Okay, I didn't define that because it was also defined in the course of Vincent Jourdain. But you can define actually 3 categories of single-wall nanotubes, depending on the angle theta. The first category is called armchair. In armchair nanotubes, theta 30 degrees. it means that the chiral vector will be along the horizontal on the sketch. We call that armchair because if you follow this line, you will have the shape of an armchair. So armchair nanotubes correspond to theta equal 30 degrees. And when you have theta equal 30 degrees, you can see that you are on the symmetric line between A1 and A2, so that for armchair nanotubes, you always have n equal to m. So this will be the first example we will work on. And another special class of nanotubes is called zigzag. For zigzag nanotubes, the angle theta here equals to 0. So for zigzag nanotubes, you have vectors which are on this line, parallel to A1. And this is called zigzag because when you follow this line, you can have you go one time to the left, one to the right, left, right, and you zigzag along this line. So we will work on these two special classes of nanotubes, armchair and zigzag. All the other nanotubes are called chiral because actually both armchair and zigzag are achiral. And you know that when a molecule is achiral, it's superimposed to its symmetric in a mirror. So armchair and zigzag nanotubes have a mirror symmetry, present a mirror symmetry, while the other classes of nanotubes, those for which the angle is not 0 and not 30, are chiral. Their image in a mirror doesn't superpose to the object. So we will make an exercise on these 4 special cases. One particular example of armchair, the 5,5 nanotubes. One particular example of zigzag, 50 nanotubes. And then we will extend the result to all the armchairs and all the zigzags. So here on this slide, I drew it in green the unit cell of one 5,5 nanotubes. Once again, if you want to define this unit cell, you start from one point, and you add 5A1 and 5A2. And then you have your chiral vector. And if you want to finish to draw your unit cell, you have to plot a second vector. Usually we call that T, like translation vector, which is perpendicular to the chiral vector and which must connect two equivalent points on the graphene sheet. So if you start from this point, which is the edge of an hexagon, you go in this direction, the next equivalent point is there. So for a 5,5 nanotube, this is the chiral vector, and this is the translational vector. When you will roll it up on itself, this will be the circumference, and this will be the unit cell of the nanotubes in the direction of the axis. So when you will beat the nanotubes, you will beat it like a crystal. You will superimpose different unit cells in the direction of the translation vector. So now, we would like to know how many hexagons, and therefore how many carbon atoms, we have in this unit cell. So we said that the relation between the number of atoms and the number of hexagons is this. NC is the number of carbon atoms. It's always twice the number of hexagons. Then you can either count the number of hexagons and the number of carbon atoms on this graph, or you can use this expression which relates the number of hexagons to the integers n, m, and to relate these different parameters, you have to use a divider which is actually related to the greatest common divider of n and m. So let's do the first together, either by counting on this graph or calculating with this expression. So D is defined as the greatest common divider of n and m. For 5,5 nanotubes, what is D? What is the value of D? which is the greatest common divider of 5 and 5? You know that? Who wants to answer? The greatest common divider of 5 and 5 is the greatest integer that allows to divide 5 and 5. Okay. D is equal to 5. So then you have to wonder if n minus m is a multiple of 3. So if D is 5, 3D is equal to 15. So is n minus m, that is 0, a multiple of 15? When you multiply 15 by something, by an integer, can you find 0? When you divide 0 by 15, can you find an integer? Yes, you do. You find that the result is 0. So 0 is a multiple of 15. Actually, 0 is a multiple of any integer. So therefore, dr, as it's defined here, you are in the case where n minus m is multiple of 3D. You are in this case. So dr, as it's defined here, is equal to 3D, that is to 15. Then you can calculate n from this expression. So please tell me how many hexagons you have in the 5 nanotubes. And you are also able to check that your answer is correct on this sketch. So how many hexagons do you find in a 5 nanotube? Yeah. You find 10 hexagons. If you have 10 hexagons, how many carbon atoms do you have? 20. 20 carbon atoms that you can count there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one you don't count because it's the equivalent of this one by one translation. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. These ones you don't count because they correspond to this one after a translation of T. So you do have 20 atoms in this cell. So let's extend this result to all armchair nanotubes. I remind you that an armchair nanotube is defined by the equivalence of the two integers n and m. So for one armchair nanotubes, you always have n m with n equal. So let's start by D. D will be again the greatest common divider of n and m. That is the greatest common divider of n and n. What is the value of D? What is the greatest common divider of n and n? Where n is an integer. That's n itself. Okay? N is both a divider of n and n. N minus m is equal to 0. Is 0 a multiple of 3n? Yes, it is. We said that 0 is a multiple of any integer, especially a multiple of 3n. So then you have to wonder if n minus m, you are in this case, n minus m is a multiple of 3D, therefore dr is equal to 3D, that is 3n. Finally, you can tell me how many hexagons you have in any armchair nanotubes. You can express the number of hexagons as a function of n. So what is the relation between big N, the number of hexagons, and small n, 2n? Thank you. In any armchair nanotubes defined as n equal m nanotube, you will find 2n hexagons, where n is this integer, and therefore you will find 4n atoms in any unit cell. We will use this result to calculate the electrical properties at the end of the course. Let's do the same for a zigzag. So you mind that the zigzag, for a zigzag, the chiral angle is equal to 30 degrees. So all the zigzags have their unit cell, which is cut in the graphene sheet in the direction of A1, the unit vector of the graphene sheet. So let's start by a 50 nanotube. When you build a 50 nanotubes, you start from the origin, you plot 5 A1, and you go to this point. So this is the chiral vector. This will give the circumference of the nanotube. And then you're looking for the T vector, the translational vector, which is perpendicular to this one, and which will connect to equivalent point. So you start from here. This point is not equivalent, because this is not the same edge. The first equivalent point is there. So this is CH, this is T, and this is the unit cell of a 50 nanotube. So let's start by calculating D, which is the greatest common divider of N and M. That is the greatest common divider of 5 and 0. So which is the greatest integer that divides both 5 and 0? 5. That's 5. Is N minus M a multiple of 3D? N minus M, it's 5 minus 0, that is 5. Is 5 a multiple of 3 times 5, that is 15? Is 5 a multiple of 15? When you multiply 15 by something, by an integer, can you find 5? No, you can't. When you multiply 15 by an integer, you have 0, or 15, or 30, but you never have 5. So in this case, the answer is no. In this case, N minus M, 5, is not a multiple of 3D, which is, in this case, 15. So if the answer is no, you are in this case, and dr is equal to d, that is equal to 5. Then, can you calculate the number of hexagons in a 50 nanotube? Yes, you can. You will find 10. If you have 10 hexagons, you will have 20 carbon atoms. And once again, you can check on this graph that you do have 20 carbon atoms in this unit cell. What about any zigzag nanotube? For any zigzag nanotubes, you will have M equal to 0. N takes any value, and M is equal to 0. So we will first calculate D, the greatest common divisor of N and 0. What's the value of D in this case? What is the greatest common divisor of N and 0? N. Is N a multiple of 3N? When you multiply 3N by an integer, can you find N? No, you can't. The answer is no. So, dr for all zigzag nanotubes is equal to 3D, that is equal to D, that is N, and therefore the number of hexagons is equal to N. So for zigzag nanotubes, actually it's the same result than for armchair nanotubes. The number of hexagons that we call here big N is equal to 2 small n, and the number of atoms per unit cell is equal to 4n. So let's try to conclude on the structure, and then we go to electronic properties. Before to conclude on the structure, I just want to show you real materials, because until now I only showed you some sketches, some draws, some ideal nanotubes. These are true nanotubes that are observed by transmission electron microscopy. So an ideal nanotubes is individual, like in this case. Its diameter here is around 1.5 nanometers. This is a true single-wall nanotubes that is individual, exactly the one we were working on the sketch. But in the reality, usually these nanotubes are not individual. because they have a large surface and they are the nanometric scales, they like to stick to each other through van der Waals interactions. And when they stick one to each other, the most dense way to pack is to form an hexagonal array. So they will form an hexagonal bidimensional array, which is sketched here. And this we call a nanocrystal of nanotubes. We call also that a nano bundle of nanotubes. And usually, when you grow nanotubes, when you synthesize nanotubes, you will find this kind of object, which is showed on this part of the graph, and not this kind of object. For going from there to there, you have to find a way to disperse the nanotubes to break the van der Waals interactions. So be careful. We are going to work on ideal objects like that, but when you go to reality, you will usually find this kind of object, and you have to find a way to disperse the nanotubes as individuals for different kind of applications. One word on multi-wall nanotubes. So here, this is an ideal nanotubes. In an ideal nanotubes, all the sheets are ideal graphene sheets without defects. So when you look at them in transmission electron microscopy, you can see straight lines parallel one to each other, where each of these lines is the projection of one of these sheets. So these lines here correspond to these lines here, which are the projections of the edges of the sheet. But in the reality, and especially when you want to prepare nanotubes at low cost, you have a large amount of defects. It's very clear on the picture, but you can see here that all the layers are not parallel one to each other. They make a given angle with respect to the axis. So these are usual multi-wall nanotubes that you can form by CVD. And in this case, you have a high defect density. So these two pictures were just to illustrate that often the reality is different from the ideal object. So now we conclude on the structure. So the question we asked at the beginning of the course is, how can we describe the structure? And the answer is, if you want to define accurately the structure of one particular nanotubes, either you have to know the diameter and the Chiral angle. But an equivalent way to describe the structure is just to define the Chiral vector with the NM integers. So in the following, when we want to speak about one particular nanotubes, either we will give the diameter and the Chiral angle, or we will give two integers, n and m. Then, when you want to describe the structure of nanotube in a sample, you also have to precise whether they are individual or if they are assembled into nanobundles. And when multi-wall nanotubes are concerned, you have to precise the number of walls. If you want to go more into details, you have to define the defect density. And also, then you can define the lengths, the impurities, etc. So at the end of the course tomorrow, we'll see how optical spectroscopy can help you to answer all these questions. Using optical spectroscopy, you will be able to measure diameter, Chiral angle, or equivalently the Chiral vector. You will be able to know if they are individual or if they are assembled into nanobundles. And you will have also an information on the defect density. How many times remain? How many times? 1 hour? It's up to 10:30, is it? Okay. So now we go to the electronic properties. So the question will be, how can we calculate the electronic properties? And to calculate the electronic properties of the nanotubes, we will use the electronic properties of graphene. So we will consider that the electronic properties of graphene are known. And actually, this is true, because theoreticians, people who make calculations, know how to calculate quite easily the electronic properties of graphene. Obviously, you have different levels of accuracy. So the most easy way to calculate the electronic properties of graphene is to make tight binding calculations. In tight binding calculation, you simplify the problem, and usually you consider the interaction only between the neighbor atoms. So today we will present results that are calculated in the tight binding approximation, which is a quite good approximation for the electronic properties of graphene. And we will see how we can calculate the properties of nanotubes, providing we know the electronic properties of graphene. So, just an introduction on the electronic properties, because I know that you come from different worlds. Some people from chemistry, some people from physics, some people from engineering, and probably for all of you, electronic properties that doesn't have the same meaning. So normally, for a chemist, when we talk about electronic properties, the chemist must think to the hydrogen atom, because it's the first and the most simple case that you learn. So when you have to describe the electronic properties of an hydrogen atom, you usually plot different levels. Each of these levels corresponds to one given energy. And on this level of energy, you will put some electrons. And they will be defined by quantum numbers. For hydrogen, which is the most simple case, you need only one quantum number here, called the main quantum number. And the other number, and this is the only number you need, because actually here you have only one electron. So from the electronic properties, you can also calculate the optical properties. And the optical properties will be calculated with respect to the transitions that can occur between these different discrete levels. And the possible transition that can occur give rise to an exchange of energy, which is expressed here on this part of the graph. So this is the exchange of energy that you make when you send one electron from one level to another level. So in the case of hydrogen, that's quite simple. The relation between the exchange of energy when an electron goes from level n to level n prime, is given by this expression. And with this expression, you can calculate all the optical properties of the hydrogen atom, that is, the absorption energy and the emission energy, which are used in spectroscopy to identify the hydrogen atoms. This is the case of an atom, of one single atom. And then you go to molecules. So when you have molecules, you will assemble some atoms, and the atomic orbitals, the atomic states, will be combined to form some molecular state, molecular orbitals. So in this case, this is a CC bond in the ethylene molecule. In this case, the hybridization of the carbon atoms is sp2, which is the same hybridization than in graphene and in carbon nanotubes, sp2 hybridization. And you see that from the S and P levels of the carbon atoms, you will form new levels, which are called, for carbon, the sigma levels, which are the lowest energy, and the pi level. The pi level, actually, in the carbon atoms corresponds to the highest occupied molecular orbital, and the pi star level to the lowest unoccupied molecular orbitals. When you want to study the optical properties of such a molecule, that's exactly the same principle than for hydrogen. You consider transition of an electron from one of these states to another one of these states. You calculate the difference of energy, and this difference of energy corresponds to the optical energies that you can measure in absorption or emission spectroscopies. So usually when you are a chemist, you are working on atoms and molecules, and you describe the electronic properties by such discrete levels. and you calculate the optical properties by considering transitions between these discrete levels. Now we go to the physics world. So usually when you are a physicist, you don't work on molecules, you work on crystals. And when you work on crystals, you cannot anymore define discrete states because you have a periodic array of atoms or a periodic array of molecules. Therefore, the electrons form waves. And these waves must fit with the periodicity of the lattice. Therefore, when you describe the electronic properties of a crystal, you have to describe the electronic levels as a function of what we call a wave vector. The wave vector is the vector that describes the propagation of waves in a crystal. So when you want to describe electronic properties in a crystal, you cannot anymore plot discrete levels. You have to plot what physicists call dispersion curves. And what we call a dispersion curves is the variation of the energy of the electrons, the electron energy, with respect to the wave vector. Once again, the wave vector described the propagation of a wave, of an electronic wave, in this case, in a crystal. And since the crystals are usually anisotropic, the dispersion curves, that is, the electronic properties of the crystals, will not be the same in all the directions. So not only the amplitude of the wave vector is important, but also the direction of the wave vector. And to describe the different directions of the wave vector, the physicists use what they call a reciprocal lattice. So I was not sure if all of you are familiar with this reciprocal lattice. So we'll try to define it briefly to recall what is the reciprocal lattice. But in this case, when you want to study the electronic properties, this is a sketch of the reciprocal lattice. You can imagine the reciprocal lattice as a lattice describing the space of the wave vectors. So this figure here describes the different directions that can take the wave vectors and the different amplitudes that can take the wave vector. So this is the case, the example of a silicon crystal or a germanium crystal. And the result is that you have electronic properties that depend not only on the level, but also on the wave vector. And they are sketched by dispersion curves like that. When you are below zero, you are in the occupied state at zero temperature. When you are above zero, which is called the Fermi energy, you have unoccupied states at zero temperature. And when you have a semiconductor crystal, you observe that between the occupied states and the unoccupied states, you have a part of the dispersion curves when there is no states at all. And you can define a range of energy where electrons are forbidden. And this is what physicists call the gap of semiconductors. So to define the gap and the electronic properties, you have to plot these dispersion curves and to check what is the range of energy around the zero energy where you have absolutely no possibilities of electron states. Okay, so now we come to nanotubes. So we have two kinds of systems, atoms and molecules, where the electronic properties are described by discrete levels. This is the discrete levels of atoms. Then they will combine together to form the discrete levels of molecules. And if you have several atoms or several molecules, you don't talk about discrete level, you talk about bands. In these bands, you have all the states that correspond to the dispersion curves. And when you have semiconductors, you find that you have a gap with forbidden states between the valence band and the conduction band. And now we ask, what is the best option to describe nanotubes? Should we describe them as molecules? they look like molecules because you have a finite amount of atoms in the unit cell, but they also look as crystal because you will multiply this unit cell and you can have lengths that are quite huge. Usually the length of nanotubes is at least 1 micron. So you can think that you can extrapolate that to infinity, and you can say you have a regular crystal with a long periodicity. So what about nanotubes? Discrete levels or band structure? And the answer is that the electronic properties of nanotubes do display both discrete levels and band structure, because nanotubes look both like molecules and crystals. So nanotubes can be seen by chemists like molecules. They can be seen by physicists as crystals. And when you look at their band structure, electronic properties, you find both some bands, like in crystals. This is the valence band. This is the conduction band. And between valence and conduction, you have the gap. The 1210 nanotubes is a semiconductor nanotube. So you observe a gap, forbidden states of energies around the Fermi level. But on this band structure, you can also find that you have some peaks here, what we call singularities, what we call more precisely Van Hove singularities. And these peaks in the band structure is not usual. It happens only when you have a one-dimensional crystal, for example, a nanotube. And this reminds you that this one-dimensional crystals also looks like a macromolecule. And in a macromolecule, you have discrete levels. And here, you can also think that you have something which looks like a macromolecules. Therefore, you find these discrete levels. So it's very practical, because chemists can say, hey, I find something I know. I find my molecular orbitals. And physicists say, hey, it looks like a band structure of a crystal. So everybody is happy, and everybody can understand the electronic properties of the nanotubes with respect to its topic. So now our work will be to try to understand how we can describe these electronic properties and how we can calculate them from the electronic properties of graphene. So I just turned my slide. Here, this is the energy. Here, this is the density of electrons. And then I make a 90-degree rotation, and I go to this. So this is the result we will have to demonstrate. First, I show you the results, and then we go to the demonstration. So first, I must underline that these calculations were made by tight binding calculations. So this is not precise calculation like ab initio. This is approximation, where you consider only the interaction between the first neighbor, maybe the second or the third, but you don't consider interaction between all atoms. You simplify the problem to get calculation on a large number of atoms. So in these tight binding calculations, you find that for all you can observe these singularities. Once again, the presence of these singularities in the density of states tells you that you have a one-dimensional system, tells you that you have a crystal which looks like a molecule. After that, you can find two categories of nanotubes. For some of them, you will observe a gap. For some of them, you will have no state, no electrons allowed around the Fermi level. Each time you have dot states around the Fermi level, you can say for sure that you have a semiconducting nanotube. But in other cases, you will find some states, not a very high density of states, but a non-zero density of states. In this case, the electronic properties will be that of a metal. When you have a continuous density of states between the occupied states and the unoccupied states, we call that a metal. The electrons can go easily from there to there. Minimum amount of temperature, a minimum electric field will allow them to go from these unoccupied states to these occupied states. So this is like a metal. And you see here that the 1010 nanotube, the armchair nanotubes, is a metal. So we will try to understand why, just by changing a very small thing, that is the chiral vector. From there to there, it's the same graphene sheet, but it's just not the same. It's just not the same chiral vector. So if you change the chiral vector, which is not fair, just a very small change, you will have a huge change in the electronic properties. It's okay? You will have a huge change in the electronic properties. You will go from a semiconducting to a metallic. This kind of nanotubes conduct the electrons very easily. So in this kind of nanotubes, you can send high density of electrons and they will flow into the nanotubes very easily. For this kind of nanotubes, you will have special optical properties. These kind of nanotubes are good light emitters in the near infrared. They have completely different properties, but they look very close one to each other. So we'll try to understand that. How can two nanotubes which are built from the same graphene sheet with chiral vectors which are very close one to each other can have such different properties? So for this, we have to talk about reciprocal lattice. To calculate the electronic properties, we have to go into the reciprocal lattice. So once again, I will try, for those of you who are not familiar with that, to give a simple definition. But unfortunately, we won't have time to go in the details, so I will try to connect that to what you already know. So usually the first time you meet the reciprocal lattice is when you make your course of crystallography. I imagine most of you have learned about crystallography. So when you have a course of crystallography, usually you define reciprocal lattice as a lattice which will be very convenient to calculate the distances between the layers, which will be very convenient to calculate the angles between the different arrays of atoms, the different lines of atoms. So first you introduce the reciprocal lattice as a very useful tool to calculate crystallographic parameters. And then when you make some X-ray diffraction, I imagine most of you had some courses on X-ray diffraction, you can define the results of diffraction in this lattice. So usually when you draw the characteristic vectors describing the X-ray diffraction experiment, you will observe the vectors of the reciprocal lattice. So the reciprocal lattice is the lattice where you can calculate the crystallographic parameters. That's also the lattice, the space, where you can interpret the diffraction experiments. Then, when you go to a course of solid-state physics, you will define the electronic lattice, and you will need it to define the electronic properties and the vibrational properties of crystals. So as I said before, this reciprocal lattice is the space of the wave vectors. In this reciprocal lattice, you can describe the properties of waves. And in crystals, you have electron waves, but also vibrational waves, what we call phonons. And to describe how the energy of the electrons or the phonons change with the wave vector, change with the direction in which you observe them, you need to work in the space of wave vectors, and you call that a reciprocal lattice. So I hope most of you have seen that sometimes, either in crystallography or in solid-state physics. So we will recall briefly how we can calculate them. And now we will work in this lattice, in this space, to understand the relation between the electronic properties of graphene and the electronic properties of nanotubes. So, to calculate a reciprocal lattice, to calculate the unit vectors in the reciprocal lattice, you have some rules. You define some rules. And these rules are reminded here. Here we have a two-dimensional crystal. So you have only two unit vectors that are used to describe the structure. Only 2 in the reciprocal space, which will describe wave vectors. To calculate B1 and B2, which are the 2 unit vectors in the reciprocal space, you consider A1 and A2, which are the 2 unit vectors in the direct space. And you use these equations. By definition, the scalar product between A1 and B1 will be a constant. The scalar product between A2 and B2 will be the same constant, and usually we take 2 pi. That's not very... When you work in diffraction, when you work in crystallography, you don't really care about this constant. But usually, when you work in the wave vector space, you take this constant equal to 2 pi. So you say that the scalar product A1, B1, A2, B2 is equal to 2 pi. And the other important rule is that when you make the scalar vector between A1 and B2, or A2 and B1, you must find that the scalar vector is 0. And when a scalar product, when a scalar product is 0, it means that the 2 vectors are perpendicular. So by definition, A1 is perpendicular to B2, A2 is perpendicular to B1. So A1 is here, B2 must be perpendicular, so it's there. A2 is here, B1 must be perpendicular, it's there. And you can see from this relation that the norm, the amplitude of this vector must be the same, but it's not the same than A1 and A2. The product of the norms multiplied by the angle between, the cosinus of the angle between A1 and B1 must be equal to 2 pi. So it's quite easy to calculate, but we don't have really time to make it together, so I give you the results. These are the coordinates of A1 and A2 in this referential, and these are the coordinates of B1 and B2 in this referential. You can see that B1 and B2 with respect to A, where A is the norm of this vector. That is the reciprocal lattice of graphene. The unit vectors are B1 and B2. You can place hexagons around the origin of the lattice. The origin of the lattice is called usually sigma. And this hexagon, which is built around sigma, is called the first Brillouin zone. Usually, you can have all the information on the waves, considering the vectors which are inside this first Brillouin zone. So, we will work in this first Brillouin zone to study the electronic properties of graphene, and then that of nanotubes. You can also see on the sketch that you can define specific points, like K points, M point, which corresponds to different wave vectors, different direction of the wave vectors, and that we will use later. So now we come to nanotubes. So if you understand well how you can build a reciprocal lattice in general, and in the case of graphene, you can also understand how we will build the reciprocal lattice of a nanotube. This is exactly the same technique. You first consider the unit vector in the direct lattice, in the real structure. We define them together. You have 2 unit vectors in the real space, which are called CH, the chiral vector, and T, the translation vector. These are the vectors we defined together before. Now, if you want to calculate the reciprocal vectors, the unit vectors in the reciprocal lattice, you have to make some scalar products between CH, T, and K1 and K2, which will be the unit vector in the reciprocal lattice of nanotubes. So you know exactly the expression of CH. You can calculate, we didn't do that together, but if we would have 15 minutes we could do that. That's not complicated. You could calculate the expression of this t vector. Like you expect, this t vector will be expressed as a function of n and m, which are the integers describing the nanotubes. dr is the common divisor, the greatest common divisor that we defined before, and a1 and a2, which are the unit vectors here. So providing you have ch and t, it's quite easy to calculate. That's just a small mathematical problem to calculate k1 and k2. So k1 and k2 are plotted here. This is k1. This is k2 in case of a 4-2 nanotube. And the mathematical expression is there. So you can show, just by resolving these equations, that k1 and k2 express like that. So they will express as a function of the two integers, n and m, as a function of dr, which is this greatest common divisor, as a function of big N, which we calculate together, which is the number of hexagons in a unit cell, and as a function of B1 and B2, which are the unit vectors in the reciprocal lattice of graphene. Okay? So at this point, it's only mathematics. It's exactly the same problem than in graphene or than in any crystal. You define a structure in the real space, and you want to describe the properties of the wave vectors in the reciprocal space. Therefore, you have to calculate two vectors, because you are in two-dimensional in this case. And this is just mathematics to go from this expression to these vectors. So we will calculate them together, just to have an idea of the expression. So that's quite easy. From this general expression, for armchair and zigzag, we'll just replace nm by n and n when we work with armchairs, and by n and 0 when we work with zigzag. And this will simplify these expressions. So when you consider this expression and you replace n and m by n and n, you can see that you will be able to simplify this. You will be also able to simplify because you know that the number of hexagons is equal to 2n. We calculate it together. So this complex expression will simplify to this simple one. For all armchair nanotubes, the first unit vector in the reciprocal lattice defines like b1 plus b2 divided by n. Same thing for if n, you have at the numerator, big N is equal to 2 small n, so n divided by 2n, it gives you a number 2 at the denominator. And this is the simple expression of the second unit vector in the reciprocal lattice for armchair nanotubes. Here is the result for zigzag. So it's not exactly the same K1, not exactly the same K2. It's normal. You don't have the same symmetry, so you don't have the same orientation of CH and T. You don't have the same expression for CH and T. So you find some slightly different expressions for K1 and K2. We will not do the calculation for the other nanotubes because it's too long expression, but it's the same logical. For each nanotubes, providing you know the unit vectors in the direct lattice, you will be able to calculate the unit vector in the reciprocal lattice. At this point, it's only mathematics. Now, there is some new physics. Usually, when you calculate the wave vector, you can describe the waves in this wave space, and the wave vector can take any values between 0, what we call the gamma point, and the edge of the first Brillouin zone, that we call the K or the M points. This is the case when you have an infinite ideal crystal in all the directions. The difference in nanotubes is that along T you have what you can call an ideal infinite crystal, but along CH you don't have. Along CH, you have a finite distance with periodic boundary conditions. So when you look at the electronic properties around CH, you have a quantization phenomenon. You are in the quantic world. You are not anymore on an infinite crystal. You are on a finite crystals with periodic boundary conditions. And because of this, all the values of the wave vectors are not allowed. It's like in the molecules. Once again, you will have some discrete states because of the finite size of the system. And because you have this finite state, this finite length, you will find discrete states. Once again, you can make the comparison with molecules. Therefore, the reciprocal lattice, or the values of the wave vectors in the reciprocal lattice in the chi1 direction are not continuous. They are discrete, and they are sketches on this graph by these different lines. So when you will consider waves propagating in nanotubes, both electronic waves or vibrational waves, the values of the wave vectors parallel to the axis will be continuous from 0 to the edge of the Brillouin zone. But in the direction of the axis, you will have some discrete states which are sketched here, which are separated one to each other by the vector k1. So now that you understand or accept this thing, you see that the structure of graphene and the structure of nanotubes are directly related. They are very close one to each other. You can define the vectors in the real space of nanotubes with respect to the vectors of the real space of graphene. So we will do the same in the reciprocal space, And because we have discrete states, we will talk about our zone folding. That's the usual name that is called for the technique we will use. We will see how these wave vectors, these discrete levels, cut the reciprocal lattice of the graphene sheet. And we will say that all the wave vectors and all the electronic states that corresponds to the position of these cutting lines will be observed in the nanotubes, and we will be able to calculate them from the electronic properties of graphene. So once again, every electronic properties of nanotubes will be calculated from that of graphene, providing that we know which are the allowed values for the K1 vectors that are the discrete lines drawn on the sketch, drawn on this graph for the 4-2 nanotube. So, I look at my watch, so I think we can go ahead. Now we come back to graphene. So we observe the reciprocal lattice, both for nanotubes and graphene. And now we have to calculate precisely the electronic states for nanotubes. And we say that we can calculate that, providing we know those of graphene. So I show you the result for graphene. Once again, this is from extended tight binding calculations. And I plot only the states corresponding to the highest occupied molecular orbital, which is called the p state, and the lowest unoccupied molecular orbital, which is called the pi star state. What can you observe for graphene? You can observe that you have states at the Fermi level, but not a lot of states. Actually, you have two discrete points which are equivalent. They are so-called K points. So you have only one state allowed at the Fermi level. From the definition we gave before, you have a metal, but because you have only one single state, we call graphite a semi-metal. It has the properties of a metal, but you have only one allowed state in the dispersion curves, in the electronic properties of graphene at the Fermi level. So now we will cut this reciprocal lattice with lines corresponding to the allowed wave vectors of nanotubes. And you will have two cases. Either when you will cut this reciprocal lattice, you will go through the K point. And if you go through the K point, this state will be allowed for nanotubes. If this state is allowed for nanotubes, you will have one possible state at the Fermi level for nanotubes, and therefore you will have a metal. But there is another option. When you will cut these dispersion curves with the allowed wave vector of nanotubes, maybe you will not go through the K point. If you don't go through the K point, you will never have an occupied state, an allowed state at the Fermi level. And if you have no allowed state at the Fermi level, your crystal, your nanotube, will be semiconducting. So because you have some quantized properties, because not all the wave vectors are allowed, not all the nanotubes will be metallic. The only nanotubes which will be metallic will be the nanotubes which have allowed wave vectors corresponding to this K point. So the nanotubes which will have a cutting line, cutting the dispersion curves of graphene on this K point. So it was mathematical to define the reciprocal lattice. It will be mathematical now to define in what case you will cut the K point with the wave vectors allowed for nanotubes. And to go from one first mathematical exercise to the other one mathematical exercise, you just have to understand that you are in a finite systems with periodic boundary conditions, that because you have a finite system, not all the wave vectors are allowed, and because of that, you will choose only some discrete single states on this graphene dispersion curve, which will be allowed for nanotubes. So let's do that together. Let's start first by armchairs. So in the armchair case, we define different things. We find that the armchairs all corresponds to n equal m nanotubes. We define that from the armchair, you have 2n hexagon in a unit cell and 4n carbon atoms in a unit cell. And we calculated that the K1 vector expressed like that in the reciprocal lattice with respect to the two unit vectors B1 and B2 with respect to n, which is the integer defining this tube. So now it's just a question of drawing. It's just a question of cutting the Brillouin zone of graphene, which is here. This is the Brillouin zone of graphene. This is the origin of the Brillouin zone of graphene. This is the edge of the Brillouin zone of graphene. This is the famous K point, which is the only Brillouin zone of the graphene where you have electronic states at the Fermi level. So we will cut this Brillouin zone according to this vector. And if, when we cut the Brillouin zone according to the vector, we cross the K point, we will have a metallic nanotubes. Otherwise, we will have a semiconducting nanotubes. So let's start with the 5,5 nanotubes. This is the vector B1 plus B2. So this vector is it, but you can shift there. It corresponds to the whole size of the Brillouin zone. 2n, when you have a 5,5 nanotubes, is equal to, n is equal to 5, 2n is equal to 10. So now you have to cut the B1 plus B2 vectors into 10 slides. Okay? And you can also observe always have a pair number. Comment on dit pair? Odd? Odd number? A pair. Odd. Comment on dit en espagnol pair? Par. A par number, par número of cutting lines. Because here you have 2n. So if you have a pair number, a par numero of cutting lines, you see that you will always have one line cutting the Boolean zone in the middle, going through the sigma k line. Therefore, you will always have a line going through the K point for all armchair nanotubes. You will always have this allowed state, which is a possible state for electrons at the Fermi level, which is the definition of a metallic system. So just because of geometry, because the geometry of an armchair nanotubes implies that you will have an allowed vector going through the K point of graphene, because of that, you will always have metallic properties for armchair nanotubes. Now we come to zigzag. So all armchair tubes are metallic. Now we come to zigzag. Oh, sorry, there is a shift of this vector. Actually, it's a vector, so you can shift it, but I would like to put it on the origin. So now you don't have the same vector. It's just mathematical. You don't have the same QL vector, so you calculate the unit vector in the reciprocal lattice. You don't find the same vector. That's just a question of symmetry, of geometry. We calculated together that for zigzag nanotubes, the unit vector K1 expressed as 2b1 plus b2 divided by 2n. Same result than for armchair nanotubes. You always have a par numero of cutting lines, but you don't cut the same way because the vector you are cutting in 2n parts is not anymore b1 plus b2. Now it's 2b1 plus b2. So 2b1 plus b2, it's 3/2 of the Boolean zone. This length is b1 plus b2. So 2b1 plus b2 is 3/2 of this. So now you have to think for what values of n, when you cut the 2b1 plus pb2 vector in 2n parts, when will you go through the K point? And you have to observe that in this case, the Boolean zone is the same, but it was rotated with respect to the armchair tube because it doesn't have the same symmetry. So when does it happen? Now it's just mathematics. You take this vector and you say, I want that an integer amount of this vector, so p times this vector, where p is an integer, will be equal to this length projected on this direction, that is the distance between the sigma and the K points. This is b1 plus b2 divided by 2. Projected here, it means times cosinus pi over 3, 60 degrees. So for the values of n which validate, which are solution of this equation, you will have one of these lines, one of these cutting lines, which will go through the K point. But if you don't validate this relation, you will have one of the cutting lines going through the K points. In the first case, you will have metallic nanotubes. In the second case, you will have semiconductors. So now it's just mathematics. So K1 is defined like that. And sigma K is defined like that. And the result is here. So the only case where one of the cutting lines will go through the cap point, the only case where you will have metallic nanotubes is when n will be 3 times an integer, that is, n is a multiple of 3. We find that all armchair nanotubes are metallic, but only 1/3 of the zigzag nanotubes are metallic, that are those for which n is a multiple of 3. We don't have time to make the same exercise on Kewal nanotubes. I just give you the results. That's exactly the same calculations, except that the mathematics are slightly more long, so we don't have time to see it in details. But I will, in my course, there will be the references of the books where we can find the solutions for Kewal nanotubes. So I just give you the answer, and you see that it's very close to the answer of zigzag, except that in zigzag, m is equal to 0. In Kewal nanotubes, it's not equal to 0 anymore. So now the condition for a Kewal nanotube to be metallic express n minus m is equal to 3p. That is, n minus m is a multiple of 3. So it's almost finished, and it's okay because we have just 2 minutes. So I will finish on this slide, and we will come back on that tomorrow. On this slide, because at this time we just demonstrated whether nanotubes are metallic or semiconducting, and now we have to go to the density of states, which is the picture I showed you at the beginning, which is here. So now now that you find which are the allowed energies of the wave vectors in the direction corresponding to the circumference of the tubes, you can calculate the dispersion curves in the other direction, which is the direction parallel to the tube axis. So here for a metallic, here for a semiconducting, these are the results of tight binding calculations. These are the dispersion curve for the electron waves propagating along the nanotube axis. And when you want to know the density of states, you just have to integrate this dispersion curve all over the wave vector range, on the whole wave vector range. So you will find two particular results. First, at each time you have a flat band, which is a zero derivative in the dispersion curves, and this happens often at the edge of the Brillouin zone. You see that here you have a zero curvature, a zero derivative. At each time you have that, if you integrate over the wave vector, you will find a singularity in the density of states. So these singularities in the density of states corresponds to flat lines, zero derivatives in the dispersion curves. Once again, that reminds you the properties of molecules. It corresponds to special states that reminds you that you have a crystal which looks like a molecule, a one-dimensional crystal. And the other important result is for the semiconducting nanotubes. When you integrate your dispersion curves over the whole wave vector range, you find that around the Fermi level, you have absolutely no dispersion curve, absolutely no allowed states. So when you integrate nothing, you find 0. And this allows you to define the band gap for the semiconducting nanotubes. So I will finish on that, and I will let you the time for question if you like. And tomorrow we will go to the rest of the course. That is, how from these electronic properties can we calculate the optical properties. This will not be very long because you already know, all of you, for molecules or for crystals, which is the relation between electric properties and optical properties. So we will just use the density of states and calculate the allowed optical transition between two different states, and this will give us the optical properties of the nanotubes. And when we will have the optical properties of the nanotubes, we will see how we can study them experimentally using optical spectroscopies. So we will recall what are the absorption, scattering, emission techniques that allow to measure optical properties. We will define especially what is Raman scattering, because that is one of the most powerful techniques to study nanochips. And at the end of the course tomorrow, we will apply the results of optical spectroscopy to different interesting questions in the world of nanotubes. So how, from optical measurements, we can describe the structure of one nanotubes. How, from optical measurements, we can characterize the dispersion of the nanotubes in a composite or the orientation of the nanotubes in a matrix. If we have time, we can also show how, from Raman measurements, we can measure thermal conductivity. Thank you very much for your attention, and if you have any question, I will be happy to try to answer. ¿Preguntas? ¿Hay preguntas?
En alguna de las otras sedes, IBIC, Mérida, Bolívar, ¿tienen alguna pregunta? La pregunta la pueden hacer en español y aquí se le hace la traducción.
¿No preguntas? Hasta mañana.
Sí. O sea, cuando uno sintetiza los nanotubos, por supuesto, siempre van a aparecer impurezas. Y esas impurezas van a aparecer en la parte de caracterización. Entonces, ¿cómo uno trata de evitar eso en los análisis? Otros materiales. Por supuesto que siempre va a aparecer el hierro como metálico cuando uno tiene en la parte de síntesis.
Okay, so if you have impurities in the nanotubes, it can be at two levels. Either it's defect on the tube itself, so like I showed for multiwalls, it's not an ideal structure, but you have defects like disclinations or pentagons or heptagons in place of hexagons. So this is the first kind of impurities. I don't know if it's this kind of impurities you're talking about. Or you can have impurities around nanotubes that are other carbonaceous species, like amorphous carbon, or graphite, or fullerenes. So optical spectroscopy will be allowed to measure, characterize both of them impurities. We will show tomorrow that from Raman spectroscopy, for example, from Raman spectroscopy, you can have a signature of the defects on the nanotubes, and you can have the signature of impurities around the nanotubes. So optical spectroscopy, especially Raman, can see these defects. So I said that you have two kinds of impurities in nanotubes. Either defects on the nanotube itself, which can be punctual defects like pentagons or heptagons in place of hexagons, or I'm not sure in English, disclinations. It means a line of defect. Or you can have defects which correspond to impurities. Because when you grow nanotubes, you always have byproducts, which can be amorphous carbon, graphite, fullerenes. You also have catalytic particles, which are not eliminated. So the question is, can we detect these two kinds of defects? And the answer is that yes, in Raman spectroscopy, for example, you can have a specific signature for the defect on the nanotubes and for the carbonaceous impurities. So we will talk about that tomorrow. By Raman spectroscopy. Raman spectroscopy. Also by microscopy, but this is not the topic of tomorrow, but also by spectroscopy.
Lo que dice que los defectos en nanotubos de carbono pueden ser de dos tipos. Uno son defectos en los nanotubos en donde en vez de tener hexágonos tienes pentágonos, u otro tipo de estructura, y otros que son impurezas relacionadas más con metales y eso que vienen del proceso catalítico de obtención, ¿no? En cualquiera de los dos casos, bueno, típicamente se puede detectar ese tipo de defectos a través de microscopía Raman o espectroscopía Raman. Claro, espectroscopía Raman por Raman, esencialmente, ¿no? Esencialmente por Raman. O sea que es una de las técnicas más usadas para caracterizar los nanotubos, ¿no?
¿Cuál es la técnica para purificar? La técnica química? Okay. So there is not no simple and ideal technique because you have many kinds of impurities. So it's not when you have one kind of impurity. Here you have several. As I said, first you have carbonaceous, and in carbonaceous you have graphite, amorphous carbon, nanoshells of carbon which surround the particles, maybe fullerenes. And then the other side you have metals, nanoparticles of metals. So you cannot purify both of them with the same process. So you have to mix processes. So as far as metal particles are concerned, usually you use acids. You use acid which will dissolve the metal, and then you rinse. As far as carbon is concerned, that's not easy because it's also carbon. So usually you try to use thermal treatments because, for example, the amorphous carbon is more sensitive to thermal treatments in air than nanochips. But if you have graphite impurities, that's very hard to eliminate. So you can use dispersion in water and then centrifugation to separate by volumic mass. So it will not be the same result for catalytic particles, for amorphous carbon, and for graphite. You disperse in a solvent and then you centrifugate because the density is not the same for the nanotubes and the graphite. You cannot use thermal treatments because graphite is more resistant than nanotubes to oxidation in air.
Bueno, dice que no hay una sola técnica para purificarlo, sí, pero no solo por eso, sino que el inconveniente es que hay varios tipos pero hay varios tipos de problemas de impureza, vamos a decir. Hay una que es asociada al proceso catalítico, que son los metales. Para eso típicamente se usan ácidos, ¿okay?, para disolverlo, pero las otras impurezas son que aparezcan otro tipo de estructuras de carbono que no... entonces, en principio, para eliminar otras estructuras se usa tratamientos térmicos, ¿ok? Pero para cuando es grafito, entonces ya ni el tratamiento térmico ni el ácido, sino que lo que se usa es que se centrifuga y por las diferencias de densidad, entonces típicamente es una forma de separar el grafito del nanotubo. ¿Bien? Por centrifugación. Sí, o sea, digamos, tú inyectas energía cinética ahí para que poder por lo menos separar a través de por las densidades diferentes.
Also, before centrifugation, you have to disperse things because they are stick together. So first you have to disperse, and before centrifugation, you use sonication. You may have to use surfactants to separate the nanotubes from the carbon impurities. So it's not only centrifugation, it's first different steps.
Sí, sí, porque típicamente las impurezas vienen pegadas, digamos, a los mismos antes de, digamos, sacar ese sistema, porque típicamente ellos tienden a... Entonces, para dispersar el sistema, el proceso antes de la centrifugación, se hace un proceso de dispersión, tratar de dispersar los materiales, y para eso se hace sonicación, y también se hace sonicación y no, pero antes de la centrifugación ya me dijo, se hace sonicación y se añade surfactantes para mantener el sistema disperso. Sí, porque el surfactante una vez, o sea, tú sonicas y después tú vas a agregar un surfactante y va a hacer que no se vuelva a pegar. Entonces después llega el centrifuga. Y cuando centrifuga tú vas a tener ya la separación, digamos, de lo que te interesa y no te interesa.
You're right. You cannot take all acids. So I think the classical recipe is a mixture of chlorhydric and sulfuric, but you have to be sure that it will not destroy your nanotubes, because if you have strong acids, you also destroy the nanotubes. And actually, you can use acids if you want to cut the nanotubes. Some people developed acid techniques when they want to control the length of nanotubes. So, okay, it's not all acids that can work, but I'm not specialist of that. There are recipes in the literature. Cutting? I said that depending on the acid you use, either you will destroy the metal particles or you will destroy both. But when I say destroy, it can be used as a way to control the length, because you will attack the nanotube first on the defects. So since the defects are statistically homogeneously distributed, if you control the acid and the time of acid treatment, you can attack at some special place and cut the nanotubes. So it's also used to control the length of nanotubes.
Sí, bueno, traduzco igual. No, lo que dice es que lo que comenta en relación al ácido dice, bueno, dependiendo del tipo de ácido se va a ir a atacar el metal o lo otro. Sin embargo, también acota que en vista de que hay defectos homogéneamente distribuidos en el nanotubo, el ácido también, dependiendo del tipo de ácido, se puede usar también como un proceso para cortar los nanotubos de carbono. O sea, que no es que los vas a destruir, sino que lo que hace es que los puedes incluso recortar. ¿Ok? Oui. Je ne sais pas si, disons, parce que bon, il y a des questions que peut-être se sont un peu de ton cours aujourd'hui, tu me dis s'il faut... Mais il me parle de la fonctionnalisation, non? Disons, il parle, disons, avec quel type de groupe on peut fonctionnaliser les nanotubes, et si par exemple, si on peut fonctionnaliser des silice, non? Cianuro. Ok, por ejemplo, que si, por ejemplo, par exemple, le cianuro, je ne sais pas comment dire. Oui. Si, disons, ça sert aussi pour fonctionnaliser, si normalement...
The most common functionalization is with COOH acid groups. So it's also after acid treatments that you can easily put COOH groups on the surface. And another common functionalization is with ODA, octadecylamine. So that are the two most well-known ways. After that, there are many, many ways, but I'm really not specialist. Maybe Alain's for sure. Tomorrow, yeah, will be tomorrow. Alain is a specialist, and probably he can answer much better tomorrow.
Bueno, él dice dice que típicamente la funcionalización se hace con grupos SiOH, ¿ah? Octadecilamina. Ok. Que son los típicos, pero que hay muchas alternativas. Sin embargo, o sea, lo que sugiere el especialista de esto es Alain Pénicaud, que va a hablar mañana. Él es el... Ajá, eso sí. No, está bien, está bien. Lo que pasa es que como ellos colaboran con quien va a hablar mañana, entonces la mejor respuesta la va a tener el otro, porque también el otro viene más de la química, ¿no? ¿Entiende, Alan? Entonces, bueno, ellos trabajan la parte de dispersión y funcionalización, es más la gente de Burdeos que tiene esa visión, pues. Y ellos de verdad, bueno, están con los grafenos y eso también. Ellos colaboran, digamos, se complementan, ¿no?